Hey everyone, and welcome to another deep dive. Today we're going to be diving into the world of realistic rendering in computer graphics. Like how those crazy realistic objects and environments in video games and animated films, how do they make them look so real? Well, that's what we're talking about today. And, judging by the stack of research papers you sent our way from, like Pixar, Sony Pictures, ImageWorks, Ubisoft, oh, and some presentations from SIGGRAPH too. You're definitely ready to get into the nitty-gritty of it all. So get ready because we're about to take a deep dive into how they bring those digital worlds to life. Okay, so one paper that really caught my eye, it's from Pixar. Those guys are like the masters of animation, especially with films like Wall-E and Up. They totally changed the game with their approach to shading. And in this paper, they actually break down their whole process, which is really cool. One of the most interesting things they talk about is this concept of lobes. So imagine trying to render light bouncing off something complex, like a dusty old copper pot. You wouldn't have one flat reflection, right? The light would be scattering all over the place because of the dust and the texture of the copper. Well, Pixar, they figured out how to copy that effect digitally using these things called, lobes.
So what's really cool is that instead of those simple models that just, treated reflections in a really basic way, Pixar, they developed a system where each of these lobes actually controls how the light reflects in a very specific direction. This lets them create really subtle and realistic light interactions. It captures those tiny details that just make the scene feel so much more believable.
That's amazing. So they're basically like fine-tuning how the light bounces around.
Yeah, exactly. And by layering these lobes, they can actually create these super complex and realistic materials. And this was huge for animators because it gave them a lot more control over how things looked without having to get bogged down with all the technical stuff.
So it's like giving artists better tools to paint with light.
Exactly. And this innovation, it wasn't just about making things look prettier, it also really sped things up.
Yeah, that makes sense. And speaking of pushing the boundaries, Sony Pictures ImageWorks, the wizards behind films like Men in Black 3 and The Amazing Spider-Man, they took a completely different approach to tackle realism in their rendering. Instead of just improving the tools they already had, they actually created a whole new language for shading called Open Shading Language, or OSL for short.
The really groundbreaking thing about OSL is how it separates how a surface should look from how the renderer actually calculates the final image.
Okay, so in simpler terms, what does that even mean?
Imagine you're an artist, right? And you want to make a super realistic leather jacket for a video game character. OSL is like having these building blocks of code. So instead of writing tons of code from scratch to tell the computer how the leather should look, you can use these pre-made pieces for things like how it reflects light, the texture, the color, all of that.
So it's like a set of special tools just for making materials.
Yeah, exactly. And because of that, it's way faster to make complex materials and effects. And that's super important for animation and games where realism is so important.
Makes sense. And I'm guessing faster rendering times means everyone's happier.
Oh, absolutely. And the speed doesn't mean they lose quality. OSL can create super detailed and nuanced materials, and that's part of what made films like Men in Black 3 look so amazing, especially those time travel scenes and all those incredibly detailed creatures.
Now, for our next stop on this realism world tour, let's head over to Ubisoft. They created the amazing open world in Far Cry 3, and they had a really interesting approach to getting that realism. When you're creating a tropical island like in Far Cry 3, the lighting has to be perfect. And Ubisoft, they were obsessed with making sure everything looked as real as possible.
The really cool thing about what Ubisoft did is that they were really serious about physically based shading. They went above and beyond to make sure the materials in the game reacted to light just like they would in the real world.
How did they do that? Did they send their developers to a tropical island or something?
Well, not quite. But they did do something pretty amazing. They used a tool called a Macbeth color checker. It's something photographers use to calibrate colors and make sure everything looks accurate.
So they used a photographer's tool for their video game.
Yep. They calibrated the colors of everything, the rocks, trees, the sand, the water, everything. They used real-world references.
Wow, that's dedication to detail.
Yeah.
But how did that actually affect the final product?
It let them use really vibrant colors without making the game look fake. It's actually one of the things that gives Far Cry 3 its unique style, that balance of vibrancy and, believability.
So it's like finding that balance between the artistic style and being technically accurate.
Exactly. And Ubisoft really showed how important understanding color and light is to making those immersive and believable worlds.
Okay, so we've talked about Pixar's lobes, Sony's new language for shading, and Ubisoft's dedication to color. Now, let's get even deeper into how it all works. Let's talk about BRDFs. I know, it sounds kind of scary, but stay with me here. BRDF stands for Bidirectional Reflectance Distribution Function. Basically, every material, whether it's a mirror or a rock, reflects light differently, right? A BRDF is basically the code that tells the computer how to simulate that specific type of reflection.
Yeah, and while there's some math involved, the basic idea is pretty simple. Think about how differently light bounces off a mirror compared to a piece of paper. A mirror has a really smooth surface, so the light reflects in a very predictable way. We call that specular reflection. But paper, on the other hand, has a rougher surface, so it scatters the light in tons of different directions. That's diffuse reflection.
So a BRDF basically tells the computer how much light should be reflected each way for a specific material.
Exactly. And by messing with the settings of a BRDF, you can create some incredibly realistic simulations of how different materials interact with light.
Okay, so this is starting to make more sense now. So are there different kinds of BRDFs? And how do they actually work in practice?
Good question. There are actually a lot of different BRDF models out there, each with its own pros and cons. Some, like the Phong model, are pretty straightforward and don't require a ton of computing power, which makes them perfect for things like video games where speed is really important.
So if I'm playing like a fast-paced action game, the computer's probably using a simpler BRDF for the environment.
Exactly, got to keep that frame rate up. But for things like offline rendering, where realism is more important than speed, you can use more complex models like the Cook-Torrance model, which is way better at capturing how light interacts with rough surfaces.
So it's like choosing the right tool for the job, right?
Yeah.
You wouldn't use a sledgehammer to hang a picture.
Exactly. And just like tools, these BRDF models have evolved over time. Remember when we talked about Pixar's layered approach with the lobes? Well, their model was actually a pretty big departure from those traditional BRDFs, and it gave them so much control over the nuances of light interaction, which is a big part of why their animations look so good.
So like they took this basic idea of BRDFs and just took it to another level.
Exactly. They found these super creative ways to improve those math models and really capture those little details that make a world feel real.
This is all so cool. But where is this all going? I mean, realistic rendering has come a long way already. What's next?
That's the big question, isn't it? I mean, as we get closer and closer to photorealism, it really makes you wonder what the future holds for realistic rendering. Like, are we going to get to a point where we can't even tell the difference between a rendered image and a photograph?
It's crazy to think about.
Yeah.
And with all the crazy advancements in technology these days, it feels like anything's possible. Do you think we'll ever get to the point where games or animated films look so real?
Yeah.
It's almost like eerie.
It could definitely happen. But even if we do reach that perfect level of visual realism, the really important question is how artists and storytellers are going to use these tools. Because it's not just about making things look real, it's about how you use that realism to connect with people on a deeper level.
Totally. It's like once you have the ability to create anything you can imagine, the hard part becomes figuring out what story you want to tell, right?
Absolutely. The future of realistic rendering isn't just about pushing the limits of technology. It's about using those advancements to tell better stories, create more immersive experiences, and, just explore new artistic possibilities.
So true. And, we've been talking a lot about how these advancements are changing things for animation and video games, but what about other fields? Like, are there other areas where realistic rendering is making a big splash?
Oh, definitely. Realistic rendering is being used in tons of cool ways that have nothing to do with entertainment. Like in architecture, they can make these virtual tours of buildings that are so real, it's like you're actually walking through the building.
Wow. So they can experience a space before even a single brick is laid.
Exactly. And in product design, they're using it to visualize and test out prototypes in a virtual world. That way they can find and fix problems before they even build a physical prototype.
That's amazing. The possibilities seem endless. We've covered a ton of ground today, from the nitty-gritty of BRDFs to the big picture implications of photorealism. But before we wrap up, I wanted to go back to something you mentioned earlier about how much research is still happening in this field.
Sure. Yeah, there's always something new to discover.
You were saying that researchers are working on new BRDF models that go way beyond the traditional methods. Could you tell us a little more about that? Like, what are some of the things that current models have trouble with, and how are they trying to fix them?
Yeah, so there's a lot of research right now focused on pushing the boundaries of what BRDFs can do. One of the things that traditional models have trouble with is accurately capturing the look of materials with complex subsurface scattering.
Subsurface scattering. That sounds interesting. What is that exactly?
It's basically how light interacts with material below the surface. Like, think about a piece of jade or a block of marble. They have this soft, almost translucent quality that's really hard for traditional BRDFs to replicate accurately.
Oh, right. It's like the light is bouncing around inside the material, and that gives it that depth and glow.
Exactly. And so researchers are developing these new BRDF models that take subsurface scattering into account, and it's really improving how realistically we can render those types of materials.
Oh, cool. So they're basically refining how the computer understands how light behaves at a super tiny level.
Precisely. These new models are all about simulating how light photons actually bounce around within a material before they're reflected back out, and that's what creates those really subtle effects that make certain materials look so lifelike.
It's mind-blowing when you think about all the calculations that are happening behind the scenes just to create that subtle translucency in a digital rendering.
It really is amazing. But that's what's so exciting about this field, you know? It's this constant back and forth between art, science, and technology, and it's all driven by this desire to understand and recreate the world around us.
And it seems like with every new discovery, we just uncover a whole new layer of complexity to explore, like this endless pursuit of perfect simulation.
Exactly, and that's what makes it so captivating. We're always pushing those boundaries, both technically and creatively.
It really is. It's
Yeah.
like they say, the more you learn, the more you realize you don't know.
I know, right? It's crazy. And that's what makes it so fun. It's just this never-ending journey of discovery, always something new to learn.
Well, I think that's a great place to wrap up our deep dive into the world of realistic rendering for today. We really went deep, from Pixar's super cool shading model to Sony's amazing shading language, OSL. And then we saw how dedicated Ubisoft was to color accuracy. Oh, and we even talked about BRDFs and all the crazy research going on there. Realistic rendering, it's clearly a field that's always changing and evolving. What started with those blocky polygons has turned into something that's almost impossible to tell apart from real life.
It's pretty incredible what people can do, you know? And as we keep going, it's not just about making things look real for the sake of it. It's
Yeah.
about using that realism to, like, connect with each other, tell better stories, and create things that we never even thought were possible.
It's like we're not just rendering images, we're rendering whole new possibilities.
Perfectly said. I think the future of realistic rendering is going to be amazing. I can't wait to see what happens next.
Me too. And hey, a huge thanks to you for like being our guide on this journey. Your insights have been awesome. And to all of you listening, thank you so much for joining us on another deep dive. We hope you guys enjoyed it as much as we did. Don't forget to check out the show notes for links to all the research we talked about. And until next time, keep those questions coming and keep exploring this amazing world, both real and, rendered.